Assalamu alaikum, everyone. This lesson is a revised excerpt of a puzzle note titled Self-Inductance. We revisit a problem that concerns a solenoid that carries a changing current. We illustrate how the energy is stored in the coil's magnetic field. So just stick around till the end of this video. Watch and learn. The question is, a solenoid 25.0 centimeters long and with a cross-sectional area of 0.500 centimeters squared contains 400 turns of wire and carries a current of 80.0 amperes. Calculate letter A, the magnetic field of the solenoid. Letter B, the energy density in the magnetic field if the solenoid is filled with air. Letter C, the inductance of the solenoid. And letter D, the total energy contained in the coil's magnetic field. Assume that the field is uniform. Shown in our diagram, the solenoid has a length denoted by small letter L equals 25.0 centimeters. It has a cross-sectional area denoted by capital A equal to 0.500 centimeter squared. The solenoid has 400 turns or windings. And the solenoid carries a changing current denoted by small letter I equal to 80.0 amperes. And target variables, we have for part A, the magnitude of the magnetic field in the solenoid, denoted by capital letter B. In part B, we are to determine the energy density in the magnetic field if the solenoid is filled with air. This energy density is denoted by small letter U. In part C, we are to compute the inductance of the solenoid. This is denoted by capital L. And in part D, we also are required to compute the total energy contained in the coil's magnetic field. This total energy is denoted by capital letter U. Before we proceed to our computations, let us emphasize the key concept that we apply in this problem. So we say that energy is stored in any magnetic field, including the field of a current carrying inductor. The magnetic energy of an inductor depends on its self-inductance and current. So moving on to our computations, starting with finding the magnetic field. capital B, using the formula. Capital B equals mu naught times current small letter I and multiplied by capital N over small letter L, where the Greek letter mu naught is what we call the permeability constant, all right, or more commonly known as the magnetic constant, all right. The permeability of free space, all right, or vacuum. And small letter I, of course, is the changing current in the inductor. Capital N per small letter L is what we call the number of turns per unit of length. So plugging the quantities into this formula, we have the value of mu naught, which is 4 pi raised to the negative 7 Weber per ampere meter times the current small I, 80.0 amperes, and multiplied by N over L, or 400, divided by 0.250 meters. So doing our math, we get the value of the magnetic field, capital B, equals 0.161 Tesla in three significant figures. So in part B, we are to compute the energy density in the magnetic field, denoted by small letter u. That is equal to the square of the magnetic field, capital B, divided by twice what we call the relative permeability of air, right? Where the Greek letter u, or mu, is equal to 1, right, multiplied by mu naught being equal to 4 pi raised to the negative 7 Tesla meter per ampere. This is what we call the magnetic constant or permeability of vacuum. The relative permeability of air is exactly equal to 1, right? Multiplied by that constant, magnetic constant mu naught. So when we substitute, we get the square of the magnetic field that we earlier calculated equal to 0.161 Tesla. Okay, square it and then divide it by twice the value of mu, or 8 pi raised to the negative 7 Tesla meter per ampere. So simplifying, we get the value of the magnetic energy density, all right, equal to 1.03 times 10 to the fourth power joules per meter cube. All right. Now, the changing current denoted by small letter I, okay, induces, okay, what we call an electromotive force, or EMF, in any circuit such as the solenoid, all right, that we are talking about here. And this induced EMF, denoted by capital V, also known as the voltage, is just equal to negative capital L di over dt, where capital L represents the inductance or self-inductance produced in the solenoid, multiplied by the rate of change in the current. So di over dt is known as the rate of change in the current. And um, the uh, the negative sign here, all right, is used or emphasized in accordance with Lenz's law, all right, which states that the direction of the electric current that is induced in a conductor, such as a solenoid, all right, is such that the magnetic field that is created by the induced current opposes any change in the initial magnetic field. So the key word is oppose, hence the negative sign in this formula. So that brings us to our next target variable, which is the self-inductance capital L, which is simply the product of the number of turns or windings in the solenoid, capital N, and that is multiplied by the average magnetic flux in the solenoid, right? Denoted here by the Greek capital letter phi sub b. And then that will be divided by the changing current, small letter I. Or inductance, capital L, can also be expressed as the product of capital N times B and A, where capital A is the cross-sectional area of the coil. All right? So plugging in the quantities into this formula for determining the inductance, capital L, we get 400 times 0.161 Tesla times the cross-sectional area 5.00 raised to the negative 5 meters squared, and then divided by the amount of the changing current, small letter I, or 80.0 amperes. So again, doing our math, we arrive at the value of the inductance, capital L, equal to 4.03 raised to the negative 5 Henry in three significant figures. When the current decreases from its maximum value to zero, the inductor acts as a source that supplies a total amount of energy, right? So here, this total amount of energy, denoted by capital letter U, is just equal to 1/2 the product of the inductance, capital L, and the square of the current, small letter I squared. That is, the energy, total energy, capital U, is equal to 1/2 times 4.03 times 10 to the negative 5 Henry, multiplied by the square of the current, 80.0 amperes. So when we do our math, we finally get the total amount of energy that is stored in the solenoid magnetic field, right, equal to 0.129 joules. Obviously, the energy that is supplied to the external circuit is relatively small. And we can attribute this small amount of energy to the relatively small amount of the self-inductance, capital L, produced in the solenoid. So that concludes our lesson for this topic. Till the next episode, mabuhay. Masya Allah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.